Welcome everyone. I'm very happy that you are here. My name is Arjen Koorevaar. I am from a company in the Netherlands, Polyworks, the owner actually. And I would like to tell you a little bit about our latest research. I understood this is a technical presentation, not a commercial one. So I'll try to give you as much information as I can in a very limited time. Of course, this will be quite an overview, so just show you what we can do. But we are also here present at the show. So if you are interested, if you want to know more about the details, please feel free to visit us. I will explain later. So did I mention my name? Well, my name is Arjen Koorevaar. So a short introduction. We are in flow analysis, and to just give you an idea what we are doing and what that means, I'll show you an example. I promised to give a live demonstration, so here we go. What we do is flow analysis for RTM and infusion. So basically, what you can do with our software is that you can do your trial injections, and for this specific part, for example, on the screen before you do it in the mold. It's actually a no-brainer, especially if the risks are high. You can try first on the computer, make a lot of mistakes, and when you do it for real, it'll work perfectly. That's the idea. Now we do this in aerospace, with energy, wind turbine blades. We do this for automotive and yacht building. So in Turkey, for example, we did the Oyster project, the 100 and 125 footer at RMK in Tuzla. Turkish Aerospace Industries is one of our customers. Metal University is a customer, and TPI Composites. So this really gives us also a presence in the Turkish market. Now, what does that mean? A flow analysis, well, this shows the results for a part, 3D, and I will explain later what this actually is. For now, it's just to demonstrate how the software works. You have the part geometry. In the part is all the properties of the reinforcements. So the permeability and the porosity are the most important parameters. And then we define resin channels. We here have injection points. That's where the resin enters the part. And we have here 3 venting points. That's where we apply the vacuum. And the software will show you how the part will fill. Oh, sorry. So here you can see in steps how the part fills. And this is a full 3D model. So this model has 3D tetrahedral elements for the reinforcement, as you can see. But we also use shell elements to model, for example, the gap between the sides of the mold and the preform. And we have line elements, tubes, to model runners and channels. Now, this is all very nice, and what you see here is the result of engineering. You are going to do this exercise up front. When you have a new part and the design is finished, you can go and do your flow analysis. And you figure out how to do it the best way, and then it goes to production. Now, one of the issues we run into is, how do you get feedback from production back to engineering? Because there is always a difference between what you see here on the screen and what will happen in the actual injection. And that's also a question we often get. How accurate is your software? And what do we do if there is a difference? So this triggered us to look into sensor technology. So back to my presentation. We have the flow analysis with our software Works, or another software, of course, we have competition. And we have designed a very robust and good injection strategy, and it differs from reality. Now, if you have sensors in the mold, you can measure what's going on, right? So we can see exactly what happens. However, the trouble is, we only have a few sensors. How many sensors can you put in a mold? In production, companies don't like to have the sensors, because the sensors means that you have wires coming from the mold. This can break down, so they don't like to use that. So you have a limited number of sensors, and you do not have much information. And if you get a signal from a sensor, what can you do? Plot a 2D graph, something like this. Let me show you. I here have some sensor output, and I could display it in a graph. There you are. So first question is, what am I looking at? Well, this is a curing sensor. So what it measures is the curing. However, what you see here is this sensor measures the resistance between two contacts. What you see here is the resin arrival. So this sensor is close to the inlet, and when the resin arrives at that point, suddenly the resistance drops. So here you have resin, and here you have nothing. This sensor is further away from the inlet. So here you have the resin arrival. Here something weird happened. I don't know what it is, but nobody could explain. Maybe some noise or disturbance, whatever. And then you see the signal develop here. You see the resistance lowering a little bit. This is about half an hour. The time needed for infusion. After this, you could keep monitoring and see that the resistance changes when the resin is actually curing. However, I needed a lot of words to show you, to explain you what a simple graph means. And still, you have no clue, because where is the sensor actually located? I told you this one is closer to the inlet, but where is it? So the trouble with the sensors is we get useful information, but just in a few locations, and it's difficult to interpret. Now, the next idea was, what can we do if we combine the two technologies? Because if we have information in a few points, we can somehow fit our model to that, so make the model, the simulation model, match the feedback we get from the sensors. And because the model is based on the physics of the process, we should get a pretty good picture of what's actually going on. And that's the idea behind the technology I'm presenting here. We can adjust the material parameters, because that's where the biggest variation is. Then we can reconstruct the full picture by matching the model to the sensor feedback. And then we can use this model, which is very good, to actually control the process. Or maybe with virtual reality, look into the future. If this is the situation now, what's going to happen in 5 minutes from now? And you can anticipate on that. Yeah. So a few pictures to show the experience we already have with infusion. So we did the Oyster 100 and 125, like I mentioned. Here you can see, I hope the pictures are clear enough, but the layout of the injection, and you can see it's a very complex set of a lot of tubing and venting points. Here is an image of the flow analysis we did for the deck of the 100-footer. And here you can see the preparation of the infusion for this deck. So in aerospace, automotive, wind engine, boat building, we also do projects. So this one is a landing gear for the NH-90 helicopter in carbon composite, made with braided preform. We have here a wind turbine blade. This is from LM in Denmark. This from British Aerospace Airbus spoiler. We did this in the start of the 90s. We are in this business for quite some time already. And here on the right you see a mock-up. This is a 75% scale starfighter built in Czech Republic. Now, having a flow analysis software and trying to link it to feedback from sensors, we wanted to do this in real time. So to have actually during the injection, get the feedback, match the model, and get a picture that shows up what's going on. Now, first of all, we needed to do this in 3D. The example I just showed you, a 3D model, is from a tidal turbine blade. These are very thick laminates. So we need to model it in 3D. We also have thin laminates in aerospace, but with a very low permeability through the thickness. So actually, the surface fills very quickly, and then it takes a long time to go through thickness. You have to model this in 3D, otherwise you don't see the details. So, because we have to do many simulation runs in 3D, we need a very fast solver. So that's the first area where we put in a lot of effort. The solver is vectorized, so it can work in parallel. However, we are limited to the speed of the memory bus, so the connection between your CPU and your memory. This is what limits the speed of the solver. So we hit that limit now, so we cannot go much faster unless you buy faster hardware, of course. And we have to work with coarse meshes. We cannot afford to use very detailed meshes, because if we do, it slows down too much and we are no longer real time. So we also need to be very flexible, because if you have a flow analysis software, it can be a single application running on one computer. However, when we connect with the sensors, we suddenly have to interact with the outside world. We have network connections, we get data from that. And of course, you have to do some last fixes on the spot. That's always happening. So we need flexibility, the ability to build custom solutions, and the solution for that is a scripting interface, for which we developed our own language, because we need multitasking features. That was the most important thing, and you cannot get that in Python or Lua or other scripting environments in the way we wanted to have that ability. Concurrency is very, very important. If we get sensor feedback, we have to always be listening, and everything else, also the simulations we are running in the background, have to continue, because otherwise, somehow, or we miss information, or we do not have the ability to match our model to the sensor data. Networking, of course, and we have quite a complex objective function, because you can imagine an infusion process has a lot of parameters. We just select a few, but still you need to be able to do clever optimizations, because still we have the real-time limit. We cannot afford to do too many iterations. And of course, for all this stuff, it has to work. So we need to have a very robust system. It's not running in a very controlled environment. We are in maybe production or semi-production development environments. So one of the things we had to solve was the 3D mesh generation to generate coarse meshes. If you want to have 1 million 3D elements, tetrahedrons, not so difficult. If you want to have a few thousand, then it gets hard. So we use state-of-the-art technology. It's fast, of course, but that's not the most important thing. We use all the technologies known right today and put it all into a very advanced mesh generation software. So it uses recursive flipping, generates Steiner points, but just a few, because if you want a coarse mesh, you don't want the mesh generator to add a lot of points to your mesh. And the major issue is in mesh generation is precision. So we use adaptive precision, and we implemented a very aggressive optimization algorithm to be able to optimize the coarse meshes. Because we have a coarse mesh, we don't have that many elements, so we have to try to improve that mesh as much as we can. So we use several technologies for that. Point location, it's optimized, not use simple Laplace smoothing, which moves every node to the center of all its neighbors. No, this is optimized to get the best quality for the worst element. That's basically what it does. And the same criterion is used for flipping elements, edge contraction. Sometimes removing nodes will increase the quality of the mesh, and also to inject new points. So I'm not going to bother you with too much of the details. The other thing we need is, if we have a coarse mesh, we don't have very nice elements. So we also need to be able to calculate reasonably accurate solutions with bad elements. So we developed a special element, a 3D tetrahedron, which has a special formulation. It's a finite element formulation, but semi-control volume. To explain that, we calculate the pressures and the velocities and the temperatures using finite elements. However, we start with an empty mold, and the mold fills, so we have to track the flow front. So for that, we use a control volume method. We have cells, and here you see a nice tetrahedron. Every node has an associated volume, and the volume is the sum of a part of all the connected elements. And we are not simply using 1/4 of every tetrahedron, but we actually use here the cutting planes sorry, to get a very good accuracy. And here you see an element which is almost a sliver. That's what we call a sliver. This element gives us the worst nightmares because it's very thin. All the edges have reasonable lengths, but calculating the pressure gradient in the thickness of this element is very, very inaccurate because you are doing it using points spaced relatively far away, and the distance is very small. However, this formulation does not break down until elements really start to have zero volume. So the question is, okay, we have coarse meshes because we want to go fast. We have 3D. How accurate is all this? Now, there's two things you have to consider. One is the numerical accuracy, because we are approximating the physical laws using the finite element method. The other part is the material properties. We have the permeability, we have the porosity, viscosity of the resin. I'm now showing you the numerical accuracy, which is, from our point of view, the best reassurance we can give you. The material parameters, well, they're different each time. So you can put a lot of effort in getting them. However, with our technology, you can also say, okay, maybe the material parameters are not perfect, but I'm going to do an actual injection and I'm going to match the model, and then I will have the right parameters. So here for 3D, this is a quarter circle. This is a worst case for the software because the pressure gradient is a logarithmic function of the radius. So that's hard to approximate with a linear element. Through thickness, we can vary the number of elements. And this graph here shows the numerical error. And you can see here that with 200 nodes, that's this point here, we have less than 0.5% numerical error. If your criterion is 1% numerical error, well, you're here. So that means about 100 elements. And numerically, you're already very accurate. You will need more elements to get sufficient resolution to see what the flow actually does. So bottom line is, you don't need to worry about accuracy. Calculation time is the other worry. And what you can see here, this graph, you have a flat part, and here suddenly you go up. This has to do with the size of the CPU cache. Our calculations are, the solver is memory bound. So as soon as your problem gets too large, you have to access the RAM memory. And even though we did a lot to streamline the interaction, we actually put hints in the code, still you see a dramatic slowdown at some point. So that means we want to stay below this point, and that's about 5,000 to 10,000 elements. So we implemented the scripting language. We called it SALT. Actually, it's based on technology which is available as a public software, open source, from Lua. And Lua is actually most used in the gaming industry. And we are engineers, we build engineering software. However, if you're going to look into graphics or scripting, the gaming industry is much more advanced than we are. So better to focus on what they use and see how we can adapt it to our purposes. Now, Lua is missing one key component, and that's concurrency, but it's small, it's very elegant, so we were able to take this and more or less merge it with our implementation of the concurrency part. So we have a very fast virtual machine. The scripting is also quite fast. Duck typing, typical for a scripting language, is not typed, so you can quickly hack something together. This is useful if you have to make some changes on the spot. You don't want to go through a big review cycle. You just want to make it work. We have closures, coroutines, tables, so a lot of high-level constructs in the language. It makes it easier to program. And we have isolated threads. So basically, we are running a lot of separate tasks which are not interfering with each other except for sending each other messaging. So messaging is the primary means of communication and synchronization. And that makes the whole multitasking part, the multi-threading part, very robust. And also, and that's the biggest issue, easy to program and get a robust system. So then we had to add networking and asynchronous I/O and our flow analysis technology. And we did that as a library. Basically, this includes all the functionality we have, and you can access it from the scripting language. So you can do whatever you want. You can generate models, but you can also do some general programming in it. So we can now run multiple simulations in parallel. We can extend functionality we already have in the scripting code, and we can also integrate our solver technology in custom applications. Now, how does the setup look like? We have here, this is more a conceptual picture than actually the test setup. I'll show you later. We have a flow analysis model, and we have some material parameters. Now, if you're going to use this, your material parameters are a first estimate. It's no longer the end of the road. It's a starting point. So we have a flow analysis, and then we get some numerical results from this. Now, we also have the actual injection. So this is the mold, and we have several sensors. And we are going to inject the resin in it, and we get feedback. So then we have another result. That's the manufacturing data. Now, comparing the two, there will be a difference between what we actually measure and what we predicted. So what we do is we take the two sets of data, calculate the difference, and try to come up with new parameters, run the flow analysis again, and this should be closer to the actual manufacturing data. So if we keep repeating this several times, we get better and better. That's the idea. Until we are very close to what's actually happening in the mold. Now, the example I want to show you, the promised live demonstration, is a tidal blade root section. Here you see a cross-section of the tidal blade. You can see the root laminate is very, very thick. So this was a major concern in the infusion of this part. And what we've taken is, we've taken this laminate and we rolled it out and put it flat in the mold. Why did we do this? Well, because we had a test mold, which basically had the shape of a brick, a big rectangle, and with an insert, we could inject this laminate. Now, the model, and I showed you at the start of this presentation, consists of the reinforcement. This is carbon fiber, modeled with 3D elements. We have surfaces around the model to model the gap between the preform and the mold, because if you have a very thick preform, it doesn't fit exactly, and even 1/10 of a millimeter gives you a lot of resin flow. So you need to take this into account. And then we have the feeding channel all around, and we also have a channel on top, because every corner in your part will be a possible cause for race tracking. You cannot compact the fibers in a corner as well as you can do it in a flat plane. And with this kind of fiber volume fractions, close to 60%, 1% change in fiber volume gives you 100% change in permeability. So in other words, if you have a 1% change, say 59 or 58% fiber volume fraction, your resin will flow 2 to 4 times faster. And that's a lot. So we have to include this kind of effects. This is how the mold looks like, the test mold. Here you see the design, and I included this picture because it shows you how many sensors we can actually put in this mold. Here you see a grid of 3 by 5 points. Every point we can use as a resin inlet, a vacuum connection, or we can put a sensor in it. And we used pressure sensors, thermocouples for the temperature, of course. We had curing sensors, and we also had resin arrival sensors. And a resin arrival sensor just gives you a signal when the resin is there, and that's it. So here you see the mold, the cavity, without the insert. So like I said, it's like a brick, a thick rectangular section. And here we have the insert in the mold, and the channel is integrated in the insert. And here you see finally the mold closed. So there is wires, there is tubes, but you cannot see what's inside. Now in the example, the demonstration I will show you, we actually did it in a workshop in the Netherlands at an airborne company, and we had a big screen and could show exactly what went on in the mold, at least what our best guess was at that moment. So for this particular part, we did a sensitivity analysis and chose 4 parameters which had most influence on the resin flow. Of course, first of all, the permeability of the reinforcement. We're not quite sure whether the numbers are correct, so we want to be able to fit that. Then we have the easy flow path here along the top. We don't know what it is. It's almost impossible to measure, so it's another variable. And then we have the left gap and the right gap, because it's possible that the preform is not symmetrically exactly in the middle of the mold. Maybe the gap on one side is 0.1 millimeters, on the other side 0.5. So with those 4 parameters, we can try to match the flow, the model, to the feedback from the sensors. And the sensor locations, and that's very hard to see in this slide, unfortunately, we have several points on top which corresponds to the locations you see here. And we can use those to check, to monitor the flow front. So this slide says future work. So now I will have to show you the live demo. Let's close this. I hope the resolution is high enough. Well, first of all, I here have the model. I'll put it right on the right of the screen. So then we have recorded the sensor data. So from that workshop, I have all the sensor data in a file, and I have this little script which will replay the sensor feedback through the network. So for the software, it will look like the data acquisition system is present. This little script is just going to fake it, and when it's running, you'll see numbers going down the screen. It's now waiting for the flow analysis software to connect. Ooh, I'm not very good with this. So here is a third script, and this is called Ecomax. So this is doing the actual fitting, and you already see the simulation running, because it's more or less doing an animation based on what we have now. So when I started, you'll see here on the left. Oh, I'm sorry. Something goes wrong. So I told you, sometimes I have to fix something on the spot, so I'm going to demonstrate that now. Direct. So this is the actual script we're using to do the optimization, and this function was changed in the last version of the software. I'm sorry about that. I should have checked before giving this presentation. It's a simple rename. So if I'm lucky, and you too of course, this will work. So let's try again. We have here the flow model. I'm going to launch virtual Nikos. We use the sensor system from Synthesites, from Greece. And keep my fingers crossed. So what you see now is, at first, not much happened. That was because there was no sensor feedback. Now there is sensor feedback. And each time there is one sensor that detects resin arrival, the system will abort the current optimization run, take the new data into account, and start a new optimization run. And you will see sometimes the simulation jump back and forward. The sudden jump indicates that there is new data which requires adjusting the model. However, I'm running it now 10 times faster than the actual injection. So there is not really enough time to get a good match. So that's why it may look a little bit jerky. But here you can see each simulation run tests a new set of parameters, and the number of parameters equals the number of sensor data we have as a minimum. Because if we have only data from one sensor, we can change only one parameter, not 2 or 3, because there is infinite number of solutions. So here you see that it's predicting the flow front's almost closed. And this we could actually check, because there is a tube at the vacuum side, and you can see resin come up. And well, I was very happy to see that we captured this moment very well. However, you see here it's almost closing. In a while from now, you will see it jump back, because based on the data from the first part, we were a little bit too fast in the prediction. So this would run for about 3 minutes. I will not bother you with everything. Just you have to trust me that we had a very good agreement and that it worked. So I will abort it now. Let's see. So, going back to my presentation. So this is what we are at now. So what's the next step? Well, the next step is we did the process monitoring part. So we showed as a concept that we can make this work. We can link our flow analysis software to the sensors, and we can match our model to what's actually going on. This would be the first step, the prerequisite for doing process control, model-based process control, because you are going to trust that the model gives you a good prediction, that you can predict the future based on past experience. Of course, that requires more work. We need more experience, we need more use cases. So now we are working with, in Holland, Technical University in Delft, for testing and validation. Students are going to build test setups different from the ones I showed you and try to improve the system. We also have students working on virtual reality, the augmented reality, to test the concept of linking this and looking into the future. And from our side, we are combining all the software we developed, so the scripting, the solver, into a completely new software, which is called ArjenWorks 4. This is our goal. I'm not sure we will finish it next year, but for sure it will be available in 2019, 2 years from now. This is quite a project, quite a big project. So to finish, I want to thank the European Union for funding our research and also all the partners in the project. We had German Aerospace Laboratories, Airborne, Bombardier, Dassault Systèmes, Vibra Hutchinson, LMS. That was when we started the project in Belgium, Samtec, and Loop Technologies from the UK, the Dutch Aerospace Laboratories, and Synthesites, who provided the sensors. So if you are interested, you can visit us in the booth of Enoris, who represent us for Turkey, at booth C3 in Hall 1, or check our websites. So thank you very much for your attention.